Hello and welcome. In this video, we're going to take a look at the supporting notes and concepts for the AP Physics 2 course, Physical Optics. Let's begin. In this section, 24.4, Frequency, Wavelength, Speed, and the Electromagnetic Spectrum. What is an electromagnetic wave made of? How do these two components relate? And how are their directions related to the direction of travel of the wave? Well, we can see from an image here that an electromagnetic wave is essentially an electric field and a magnetic field running together. The magnetic field runs in this direction, and the electric field runs in this direction. In other words, the two fields are perpendicular to each other, while the direction of each transverse wave runs in that direction. They're produced because changing electric fields can produce a magnetic field, and changing magnetic fields can in turn produce an electric field. So this is known as a self-propagating wave. They usually originate from stars that undergo nuclear fusion. One of the byproducts of nuclear fusion is electromagnetic radiation. What is the relationship between the wavelength, frequency, and speed of an electromagnetic wave? The equation we use to relate these variables is C is equal to frequency times wavelength, where C is the speed of light in a vacuum, with a constant value of about 3 times 10 to the 8 meters per second. Name 7 different types of electromagnetic waves in order from lowest frequency to highest frequency. Well, starting at the lower end of the frequency, going from small frequency to large frequency, which by the way goes from large wavelength to smaller wavelength, we begin with radio waves. Radio waves would be television signals, GPS signals, low wavelength cell phone signals, things of that nature. Microwaves, infrared radiation, visible light, which, as the name would suggest, is the only form of light we can see, UV, which stands for ultraviolet, X-rays, and gamma rays. All 7 forms of radiation are 7 different forms of light. Only visible light, of course, is what we can see. What is the range of visible light for frequencies? Well, the visible light spectrum ranges in terms of red, orange, yellow, green, blue, violet, from about 400 nanometers on the blue-violet side to about a little over 700 nanometers on the red side. Ultraviolet, which is a little bit lower than this, ranging from 200 to 300 nanometers, is not visible. Infrared, ranging from 800 to, let's say, 1,000 nanometers, is also not visible. Section 24.1, Polarization of waves. Polarization refers to waves that vibrate in very specific directions. Sunlight, for instance, would be considered an unpolarized wave because sunlight can vibrate in any and all directions. So let's say you take that sunlight and you pass it through, let's say, vertical or horizontal filters. These filters are called polarizers. So let's say we take some unpolarized light entering the filter. And if it's a vertical filter, that means it's going to allow vertically polarized light to keep going. But it will filter horizontal light or prevent horizontally polarized light from continuing. Similarly, if we have unpolarized light reaching a horizontal filter, it will continue to allow horizontally polarized light, but it will filter or prevent vertically polarized light from going. Now, if we take filters and we orient them 90 degrees relative to each other, you will see that there's little or no output of waves passing through, meaning we have completely filtered vertically and horizontally polarized light. Let's take a look at the following video. In this first video, we can see a slinky that has a horizontally polarized filter placed right in the middle. And it's a box. It's a horizontally shaped box to allow horizontally polarized waves to pass through, but prevent vertically polarized waves from doing so. Let's take a look at this video. So in experiment 1, we're going to shape the rope through a vertically oriented box. This is a vertical polarized filter. You can see the vertically polarized wave passes through the vertical filter. No problem. Now if we turn the box 90 degrees, you notice that a vertically polarized wave will not really pass through a horizontally polarized filter. In other words, the horizontal filter has eliminated most, if not all, of the vertically polarized wave. In this second video, we can see a filter, a polarizer filter, placed in front of a light source, and the light source is connected to a meter to be able to read off the luminosity or the light intensity. Notice that placing the filter in front reduced some of the light intensity. We can see that on the meter. Now if we place two polarizers together and we rotate them 90 degrees relative to each other, you can see it is almost completely eliminating the light source. And that's because we're eliminating horizontally and vertically polarized light simultaneously. And so polarization, again, just refers to waves vibrating in very specific directions. And polarization, of course, is the property of those waves that describes the orientation of those oscillations. So what does this imply about the nature of light? Well, since only transverse waves experience polarization, we therefore have evidence that light waves are indeed transverse waves. So let's take a look at a couple of applications. Let's take a look at how polarized 3D movie glasses work. Well, it starts off with two different cameras, each with a specific polarizer placed on the lens. Each polarizer is shifted 90 degrees relative to each other. These two cameras shoot an image from different perspectives. Now, when a 3D projector produces these images, they will produce two distinctly different images because we have two projectors, one for the left picture, one for the right picture. And each of those projectors will also have polarizing filters that are 90 degrees relative to each other placed on the lenses of those projectors. These two images will reflect from a metallized screen to the theater viewers. And the theater viewers are, of course, wearing polarized glasses. Each of the polarized glasses will, in turn, have a left eye and a right eye with polarized filters, also 90 degrees relative to each other. In other words, each eye will see light passing through it slightly different to create depth perception or a three-dimensional image. Polarized sunglasses work very similarly. We have unpolarized light from the sun that bounces off and reflects from some non-metallic surface. It could be the fiberglass hood of a car in front of you in traffic. It could be the glare of the sunlight coming off of the water. But either way, when the light reflects off of the horizontally positioned surface of a non-metallic surface, then what's going to happen is that reflection is going to be mainly, not completely, but mainly horizontally polarized light. So what we get is we use polarized lenses, which essentially are vertical polarizers. So if you imagine a bunch of vertical slits in the polarized lenses here, well, that would only allow vertically polarized light, or at least what's left of the vertically polarized light that didn't get completely reduced off reflection, to pass through the sunglasses, but completely, almost completely eliminating horizontally polarized light. What does this do? This greatly reduces the glare. Section 20.6, Superposition Principles and Skills for Analyzing Wave Processes. When crest and troughs of two waves interfering waves are aligned, we say that those waves are constructively interfering with each other. And you can see one wave completely aligns with the other wave. When crest and troughs of two interfering waves are completely misaligned, we say that those two waves are destructively interfering. So let's take a look at these diagrams here. In the first diagram, we can see that these two waves are destructively interfering because a crest from one wave is meeting a trough from the other. And they are essentially 1/2 a wavelength off from being aligned. So they're 1/2 of a wavelength misaligned. Similarly here, we're 1.5 wavelengths misaligned, or 2.5 wavelengths misaligned. And so the common feature here is to be misaligned or destructively interfering, you are noticing a difference in the path lengths of these waves of some multiple of 1/2 a wavelength, right? 1/2, 1.5, 2.5, 3.5, or so on. Whereas if you look at the bottom sets of waves, you'll notice that they are completely aligned. Okay, so the path difference between, let's say, this wave and this wave is 1 wavelength apart, 2 wavelengths of difference, 3 wavelengths of difference. And so what we're noticing is that to be constructively interfering, you must essentially have two waves that are differing in multiples of a wavelength. If two identical waves interfere, then the two waves will constructively interfere if they have a whole number of wavelengths of phase difference. However, if the waves are 1/2 a number of wavelengths phase difference, the two waves will destructively interfere. Okay, state Huns principle. I know that's a very difficult name to pronounce. The man was Dutch. It's pronounced Huns. I guess the Y and the G are a little bit silent. Use the diagrams to assist. Well, Huns principle suggests that every point on a wavefront is itself a potential source of waves expanding from that point, meaning every point on a wavefront could be considered a small spherical wavelet, basically. And that helps explain not only wave interference, but it also helps explain wave diffraction around barriers. What is diffraction? Well, diffraction represents the properties of a wave in which the wave spreads out or bends around a barrier. So let's take a look at Huns principle and see how that can be used to demonstrate diffraction around both sides of a barrier. So if a wave passes through a slit like this, how does Huns principle show diffraction around this side and around this side to create circular waves through the opening? Let's take a look at a short video.
So you know that we can describe light by rays that go like this, and we've done a lot of that in optics. We can also describe it by wave fronts, where I guess that's the top of each wave, and it's kind of like crest, and then crest, and then crest, and that's cool. So I want to talk about waves in terms of wave fronts coming into a barrier. So here is a barrier where waves come, and you can do this with water. It's really easy with water, and here are some wave fronts coming in. Wave front, wave front, wave front, wave front. So I guess that means that the rays are normal to the fronts, so the light is coming in here all parallel. It must be from a source very far away, or it must have been collimated or something. But Heron's principle, Heron's, oh boy, that's hard to say. Huygen. This is Heron's principle, and he says, this is extremely profound, he says that every point on a wave front is a source of spherical waves at all times. So every point on this wavefront here is creating a new spherical wavefront. So what's happening as we reach this barrier is that all of the wave here is being blocked, and all of the wave here is being blocked, so we're able to actually see Heron's principle at work. These locations right here are very close to each other, and they become locations from which a new wave springs, and that's why sound can bend around a corner. Perhaps you didn't believe that sound can bend around a corner. Perhaps you never believed that sound was a wave. Well, let me prove it to you. I'm going to go around the corner. I'm literally going to be on the opposite side of this door, and you can still hear me. Yeah, I'm quieter, but it's not reflection that you're hearing. Primarily, you're hearing the sound bend around. If we were to set this up really clever-like, I could make you another little barrier over here. Let's say I make a barrier in this big old room. I make a barrier right here. And what's going to happen is, maybe I should angle a little bit more gently. No, it's cool. Every point on here, I'm going to have this coming in like this, and it comes in like this. And this location right here becomes a new wavefront, and now I've got waves that come out like this. They're supposed to have the same wavelength all the time if I'm in the same medium, so this should be the wavelength, and it should be equal to this wavelength that's over here. But notice that now I've got waves that are going back when my original waves were going this direction. I hope that doesn't bother you. It's a little bit weird, but Heron's principle is really, really weird when you try to apply it to a wave that's just a plane wave like this, just moving in. And let's see if we can make some sense out of that. But here's Heron's principle at an interface. Wait, this means some really cool things for us. This means some really cool things. Well, we'll look at that in just a moment. First, we have to figure out how a plane wave can be represented by Heron's principle. I'm going to study 3 locations on this plane wave. Nah, 4. This one, this one, this one, and this one. And if I treat each of these as being a source of new waves, then I'll say that, well, here's the wavelength, right? So I'm going to say that right here, it will make a new wave. Right? And right here, this one will make a new wave that's like, hang on just a second, like that, right? Going out like that. This one makes a new wave that's going out like that. This one makes a new wave, sorry, this one makes a new wave that's going out like that. And this one makes a new wave that's going out like that. Now, the interesting thing about this new wave that's been formed by each of these 4 points here is that we're going to get constructive interference right here at the front. And the cool thing is that a moment later, this wave became that wave, and this wave becomes that wave, and so that's the progression of the wave. If we've got a flat wall here and a flat wall here, that wave's just going to move right on through, and Heron's principle is simply a statement that plane waves can move unimpeded. But if you get to a break where only one of these new wave fronts, these new spherical wave fronts, is able to get through, it's then that you see that a plane wave is actually made up of an infinite superposition of spherical waves. Whoa. A plane wave is an infinite superposition of spherical waves. That's pretty cool. The next thing we need to do with Heron's principle is give you a barrier that has 2 gaps in it, and then we're going to have ourselves a very interesting experience. This was Young's idea. It was 1804. Lewis and Clark were out to explore the, what was he going to do? Was it 1801 or 1804? I don't know. I'm getting some conflicting opinions, but anyway, we were certainly about to buy the Louisiana Territory, or had just bought the Louisiana Territory or something in the United States. And sometime around there, this fella named Young over in England had a great idea. He was so brilliant, he deciphered, check this out, this guy deciphered the freaking Rosetta Stone. And founded that software company. Just kidding. He actually deciphered the actual Rosetta Stone. And if I have waves coming in here, and the waves, well, they're coming from this direction. If waves are coming in here like this, then I'm going to see Heron's principle right here. I've got a new spherical source of waves here. And let me just draw one more wave. At the risk of becoming incredibly complicated, I'll draw even another. And we have a spherical source of waves right here. And remember, I have to try to get these to be the same wavelength. That's always a little bit complicated. We've got two sources of monochromatic and coherent light. And if I continue drawing these, you will see that we have regions of completely constructive interference right up the middle. If I draw one more, I guess you'll believe me there. Watch that. Yeah, and we've got completely destructive interference where the, oh my goodness, look, I got constructive interference here. I got constructive interference here. I got constructive interference here. I got destructive interference, let's draw that in orange, where trough meets crest, right in the middle there, and right in the middle there, and probably right over here also, and then some more constructive interference there. Wow! Wow! So waves can interfere with themselves if you let them go through two slits. We'll do Young's double slit diffraction experiment in the next slide. So you'll have to, the next video. You'll have to wait for that. Bye.
Section 23.1, Young's double slit experiment. So Thomas Young performed a very important experiment in the early 1800s. And what this experiment showed, what he essentially did is he covered a piece of glass with black paint and made very small slits very close together using a blade, and allowed sunlight to essentially pass through those slits. And here's what he was trying to here's what he postulated. If you have your slit, say this is your barrier, and let's say those are your two open slits. If your light is passing like this, as rays of light towards the slit, and you had a screen behind it, and light behaved like a particle or a series of particles, then what you would expect to see is you would expect to see two regions of light cast on the screen behind it. But that didn't happen. Instead, what he noticed was something really interesting. He noticed that there were regions of bright light separated by no light. We call these regions of bright light bright fringes. Separated by regions of no light in between, call those dark fringes. So let's take a second to break down what his experiment looked like and what the variables are involved. We'll take a look at a mathematical relationship of these variables, and ultimately why is his contribution, his experiment, so important to the study of light and how light behaves. Here we go. We have several different diagrams. In diagram 1, we have a wave fronts with a wavelength of 1 unit long. Okay, you can see, but based on here, everything is 1 unit right here. So you can see, based upon this, the wavelength, this lambda right here, is only 1 unit long. And obviously it remains 1 unit even after the fact. Now, each of those wave fronts, if you recall earlier, we talked about Huns' principle, in which case your wave fronts are really just an infinite number of possible points, each of which is contributing circular waves that essentially rather interfere with each other, but also they create the possibility of bending around barriers, and they allow for concepts like diffraction and refraction to occur. And so what happens, according to Huns' principle, we see that those plane waves, those wave fronts, approach the 3 boundaries here. There's 3 boundaries here, here, and here, which form 2 openings or 2 slits. When the waves pass through those slits, what they do is they create this bending effect. The light diffracts around this side over here and around this side over here. And these waves from this boundary right here, from that opening, are going to interfere with the waves created from this one. And so what we're interested in is we're interested in where the waves are meeting. So let's take a look at that. Where the waves meet together and where the circular waves cross each other, that would be a region of constructive interference, kind of like where a crest is meeting another crest of a wave. And so I'm going to highlight those regions. Here would be one. And so this would be a region that shows up as a bright fringe on your screen. We're looking at a top view of the experiment, by the way. This would be your slit, your barrier with the slits. This would be a spacing. So if we're talking about some of the variables involved here, we need to be able to measure D, the distance between the slits, okay, which actually I think would be more that distance right there. So the distance between the slits, we need to be able to measure the length, L, to the screen itself. And then lastly, we need to be able to measure X. Sometimes it's called Y, it depends if it's horizontally or vertically placed, but X or Y represents the distance between adjacent bright fringes. Now you can see here's another bright fringe right here. Here's another bright fringe right here. Right? You can see where they end up shining on the screen behind it. Here's another bright fringe right here. And here's another one here. Right? And you could keep extending it on and on. And one thing I hope that you guys notice is that the spacing, well, it's all the same. In other words, if this is the distance X between adjacent bright fringes, well, that's the same distance between those ones, those ones. And more importantly, it's also the same distance between adjacent dark fringes too. Something to consider when we do our analysis. Now you can see something's happened in this one. The wavelength is larger. Okay, so we're increasing the wavelength each time. Okay, and we're keeping, in this experiment, we're going to keep the slit spacing, this distance D right here. We're going to keep that the same. But we're going to make the wavelength a little longer. Well, what happens? Well, the interference pattern that shows up, we have a bright fringe right here. We've got a bright fringe right here. We've got a bright fringe that shows up over here, and so on. But if you look carefully, guys, this is, oops, very wide over here. This one is wrong. It would be a little wider. Okay, so what you're looking at, guys, is you're looking at fewer bright fringes. The distance between bright fringes, X, has increased. So what does this tell you? X is directly proportional to lambda, the wavelength. As wavelength goes up, so does the distance between fringes. Now what we're going to do is we're going to keep the, we're going to increase the wavelength, kind of. We're going to use the same experimental model, but this time what we're going to do is we're going to increase D. Both cases, we're going to increase D to 8 units, from 4 units to 8 units. What happens when that happens? Let's take a look. My pattern for the first one, we've got the middle, you've got this bright fringe, you've got, let's see here. That bright fringe, that bright fringe, that bright fringe. I got this one, this one, this one, this one. And as you guys can see, what's happened is the distance X has gone down. So if we compare from above, look what happened. We made D, the distance between the slits, twice as far. And when we've done that, the distance between bright fringes has gone down, and it's allowed for more bright fringes to show up on the screen. So we've got another relationship going on there, and let's just kind of qualify that by looking at this one here. Right, and you can see these are the two adjacent bright fringes. You look at the one up top, and you look down here, X has decreased as well from what we see over here. And you can see when you only had 3 bright fringes on this screen, you can see 5 are now visible because the distance between the fringes went down as the slit spacing distance D went up. So what can we conclude now? That X is inversely related to D. Okay, so far, here's what we have. We have that X is proportional directly to lambda, but inversely proportional to D. Okay, that's going to be our first set of variables that we're going to relate. Now, the basic equation for constructive interference, when we kind of put this all together, will also relate to one more variable, and that is this here, the distance from the slits to the screen. Okay, and that varies as well. And so before we take a look at the equation here, let's take a look at a physics Java applet, an animation, to see how these variables kind of relate to each other. Let's take a look at Young's double slit experiment in action. As you can see, we have a violet laser source passing through 2 small slits closely spaced together at the bottom of the screen. And if I rotate this around, you can kind of see how that would result. I'm going to look at it from the top view so we can kind of get a better vantage point. Now you'll notice that the wavelength is very small. It's at the violet end of the spectrum, almost ultraviolet. The screen distance, the slit to screen distance is L, so wavelength is lambda, the slit to screen distance is L, and the distance between the slits is D. What I want to do is I want to focus on these one at a time to see how does it affect X. Now we can see if X gets bigger or smaller. X is the distance between bright fringes. As you can see, there are currently 5 bright violet fringes showing on the screen. We can qualitatively see whether or not X is going up or down by noticing the number of bright fringes. In other words, if we have more bright fringes on the screen, that means X went down so that you could fit more on the screen. If you see fewer bright fringes on the screen, that means that X, the distance between bright fringes, got larger. So we're going to qualify X based upon how many bright fringes you see, and we're going to compare it to the number 5. So right now I see 5 bright fringes on the screen. If I increase the wavelength, you can see I'm going, and not only am I going through the colors here, but the fringes are getting farther apart. And I'm seeing fewer of them. I went from 5 to 3 to when I get to red, I barely see 3 anymore. So that as the wavelength goes up, the distance between bright fringes goes up. And we already saw that in the notes we were previously taking. How about the distance between the slits? Let me move this back to the violet end. So if I keep the wavelength constant, right, but this time I focus on D, the distance between the slits. If I make the distance between the slits larger, farther apart, you can see I'm getting more and more bright fringes, which means X, the distance between bright fringes, is going down. So as D goes up, X goes down. That's an inverse relationship. We already saw that. But what about L? L is the slit to screen distance. It's how far the slits are away from your screen. So right now, if I increase L, well, there we go. If I increase L, notice I went from 5 bright fringes, and as I increase L, I'm down to 3 bright fringes, and then pretty much just 1. So what's happened is, as I increase the slit to screen distance, That means I'm getting fewer bright fringes. That means the bright fringes are spreading farther apart. That means X goes up. Now let's take a look at it in terms of the intensity and the energy that is showing on the screen. I'm going to change this from experiment to results so that you can see. Again, we've got 5 bright fringes on the screen, 1 in the middle, 2 outside of that, and 2 outside of that. And so you can see, according to the graph below, every time we have a maximum value, a maximum intensity, that is corresponding to a bright fringe. Every time you have minimum intensity of light, meaning no light, you have a dark fringe. So we have dark fringes in between each bright fringe. And that would correspond to a minimum intensity on the graph. Again, if I increase the wavelength, what does that do? It spreads my maximum out. It spreads my bright fringes farther apart. If I increase my L, my slit to screen distance, the same thing happens. My bright fringes are getting spread farther apart. Notice, still keeps the same amount of energy. The intensity of the energy stays the same. What happens and what changes is how far they are spread apart, because each maximum minimum correspond exactly to the location of a bright or dark fringe on the screen. And again, lastly, is if I change the distance between the slits, you can see I'm adding more bright fringes, which only means my minimum and maximum points on the graph are just simply closer together. Also notice how the maximum of the graph pretty much remains similar intensity all the way throughout a double slit experiment. Now we're going to see something different when we look at a single slit experiment. So now if we put this together, our basic proportionalities, X is directly proportional to the wavelength. So the distance between bright fringes goes up as the wavelength goes up from violet to green to red. So as the wavelength goes up and changes the colors, so does the spacing between the bright fringes. X is directly proportional to length. If you make the length farther, if you make the slits farther apart, then if you make the screen farther apart, move the screen back, the slits are going to show bright fringes that are farther apart as well. But also that if we make the slits farther apart, that is inversely proportional to the distance between adjacent bright fringes. And so if we put this all together, we get that X is equal to m lambda L over D. This is our main basic equation for what is called constructive interference. So now, what is M? Well, M essentially is an integer multiple Okay, that's what it is. And it basically tells you which bright fringe you're talking about. So for instance, if we're talking about the first one, the distance to the first bright fringe, so we'll go back to the picture. This is 0 right here. Get rid of this part right here. This one here would be m equals 0. This would be m equals 1. Think of it as the first bright fringe from the central maximum, from the central line. It's the first bright fringe from the central line. Here, this is m equals 2. It's the second bright fringe. This one's m equals 3, and so on and so forth. M equals 4. And the same pattern applies on the other side. This is m equals 1 because it's one bright fringe away from the central maximum. This is m equals 2 because it's the second bright fringe away from the central maximum. This is m equals 3. This is m equals 4. Quite honestly, you don't really need to use your integer multiple unless the question specifically states how far from the central maximum is the third or fourth bright fringe, What is the distance to the third or fourth or fifth or 10th bright fringe? Then you would use the integer multiple m. If you're just looking for the distance between adjacent fringes, you don't worry about m at all. Okay, so again, something to note when looking for the distance between adjacent bright fringes, just let m equal 1. Just let m equal 1, because if you look, that's exactly what it is. The distance to the first bright fringe is m equals 1. Okay, that's the integer multiple we would use. And that distance right here, this distance to the first one, corresponds to the distance between any bright fringe, the distance between any of them. Okay, now to find the locations of destructive interference, well, really you use the same equation, to be honest with you, but let's say you want to find the actual location to a specific bright fringe. Well, then what you do is you set m equal to multiples of 1/2 lambda. Okay, so the equation becomes x equals m plus 1/2 lambda L over D. Okay, where if you're talking about the first dark fringe, right, the first dark fringe, that is essentially, that's going to be halfway. If you notice, the first dark fringe is halfway between the distance between adjacent bright fringes. So the distance to the first dark fringe, that's half a wavelength of difference. This is 1.5 wavelengths of difference, or 3/2 of a wavelength. This is 2.5 or 5/2 of a wavelength of difference. And what does that mean? It means if you had a wave that was this long, okay, let's say you have a wave that's that long, and you have a wave that's this long. This wave right here is half a wavelength longer than that wave right there. That's what that means. So let's do a couple problems. Let's find out. Find the m equals 2 angle, okay, for the upper left diagram. Okay, so we have another equation that we're also going to be using, so let me derive that one as well. Okay, and here's the equation. Let me jump down a little bit to derive it, and then we'll come up back here and use it. Okay, so let's say we have, and I'm going to use 2 sound speakers, and we'll focus on sound interference, but really it applies to light interference as well. It's just the interference of waves. So say you have 2 speakers that are one source, and then here's another source right here, and you can tell that these, like, so this speaker right here, that wave is 7 meters long, and it's 3.5 wavelengths long. This is 11 meters, and it's 5.5 wavelengths long. And you can tell that they're meeting in phase with each other because they're meeting at the same spot. This crest goes with that crest. This crest goes with that crest. That trough goes with that trough. They're in phase with each other. So what you notice with that is there is a difference. If you subtracted that, there is a difference in the path. This path and this path have a difference of 2 lambda, right? There's a difference of 2 lambda there to get destructively or constructively interfering, excuse me. Whereas this one here, if we take a look at this one, that wave, 11 meters long, 5.5 wavelengths long. This one is 6 meters or 3 wavelengths long. You have a trough meeting a crest. They're destructively interfering, right? And notice the difference between these would be 2.5 wavelengths, or 5 halves lambda. So when you have waves that meet, and they meet with some whole number integer multiple of the wavelength, your waves will constructively interfere, and if it's sound waves constructively interfere, you'll get a louder and more intense sound at that point. If it's light interfering, you'll get a brighter light at that point. If you're talking about two waves destructively interfering, two sound waves would essentially cancel out, and you'd get minimum sound intensity. If you're talking about light cancellation, then you'd get the opposite of light, of course, is no light. It would be, no light shining in that area. Could translate into, absolute darkness, or just simply no bright light at all. So what does this new equation look like? Well, here's more or less what we can visualize. Take a look at this picture. So say we have the central maximum right here going down the middle. All right, and let's say we have this over here. Well, what we have is we have a similar triangle that's set up with this, okay? And I can actually do this by taking a look at this picture that's set up here. Let me change the color. So here's one path. Here's one path. And here's the other path. Now, if I were to essentially draw a line going down like this, okay, I have myself a right triangle right there. And this right here is D, the distance between slits, or in this case, the distance between speakers. What you're looking at here would be angle theta, and what you're looking at here, okay, is opposite. That would be d sine theta. And what is d sine theta equal to? Well, it turns out that d sine theta is essentially equal to the difference in your wavelength. So we have a new equation that we can set up, and that is d sine theta equals m lambda. Now, if it's destructive interference, it would be m plus a half times lambda. Okay, but we're going on an even integer multiple, not just even, but a whole number integer multiple. So this would become, if I'm looking for theta, this becomes sine of my angle equals m lambda over d. Oh, wait a minute, that looks very familiar. M lambda over d. Oh yeah, that's that. So that means if I take that equation and I divide length both sides, oh, wait a minute. Okay, so that means x over L equals, what does x over L equal? Look at this right here. X over R is the sine of theta. But if theta is very, very small, then what happens? R approximately becomes L. They become the same thing almost. And so this approximates the sine of the angle, which, as you can see, approximates this right here, m lambda over d. So this is how we can derive this new equation, d sine theta equals m lambda. Okay, so now let's go ahead and solve for theta. First, let's plug in for the sine of theta. That would be the easiest way to start. So we're looking at the second bright fringe. Lambda is 1 unit over d, which is 4 units. And so we get 1/2. If I take the arc sine of that, theta would be the arc sine of 0.5. We get roughly about 30-degree angle, roughly. Okay, so in other words, if I look at this right here, this right here, that angle right there, that separates the way, the direction, the two constructing, interfering, rays of light, the path that those are going, is essentially spaced out about 30 degrees apart. That's ultimately what we're getting at. All right, so now what about in the lower right? So here, d sine theta equals m lambda. So sine theta is equal to m lambda over d. So m is 4 this time. Lambda is 2, spacing of 2. And d, the distance, is 8. So, well, this one's easy because you have 8 over 8. And so we get 1. Well, when you take the theta, see, when I take the arc sine of 1, I get about 90 degrees. Let's look at that. Now, we're talking the distance, and I misspoke on the previous question. This 30 degrees is not, ultimately not what I'm talking about here. Let me fix that. What I did is I accidentally found the distance to the first bright fringe. But if you remember the calculation, we were looking to m equals 2. So this is m equals 1 right here. This is m equals 2. So we were looking at this. That looks better. That is about a 30-degree separation in terms of the direction of those interfering light rays. But if we look at this one here, and we're looking at, this is m equals 0 in the middle. This is m equals 1, m equals 1, sorry, here, m equals 2. And you can see if we spaced it out, it's spacing out about this far. This would be m equals 3 way over here, and m equals 4 is way down here, right? There's m equals 4 way down there. And look at that. This, okay, you're all the way down here to get to the next one. Yeah, that's pretty close to a 90-degree angle. Okay. Doesn't quite show up on the screen very well when you get to that point. So again, for the triangle here, the right triangle is x over r. If you look right here, the sine of the angle would be opposite over hypotenuse. But for the small angle approximation, it really becomes x over L, because if this angle gets really super small, then this side essentially is the same length as that side for all intents and purposes. Okay, so your new two-source equation would be d sine theta equals m lambda. Okay, that would be for constructive interference. So CI stands for constructive interference. And then how would we write this for destructive interference? Well, it would just be m plus a half times lambda. It would be half integer multiples of lambda, not whole integer multiples. And I guess that's kind of a misnomer. There's no such thing as a half integer. But basically, half of a wavelength is what we're talking about. Multiples of half a wavelength as opposed to multiples of a whole wavelength. Describe Young's double slit experiment, what he did, what he observed, and the implications for understanding the nature of light. So now let's examine why this was so important. Well, Young passed sunlight through an opaque surface with small slits very close together. If the lights passed through the two small slits and showed up on the screen behind the slits, then the light was made of particles. However, he postulated that that was not going to be the case. He understood Huns principle, and he understood that every point on a wavefront, there's an infinite number of points on a wavefront that can produce circular waves. So there is so much possibility for not only interference of waves, but also the diffraction of waves around barriers. So already understanding that, he had an idea and postulated that that was not going to be the case. And sure enough, it did not. Instead, there was a repeating pattern of light and dark bands called fringes on the screen. The result of light diffracting around the edge of each small slit and interfering with each other. Since Young's double slit experiment indicated the presence of overlapping waves, this means that light, since light interfered with light, light must be a wave. That is the important conclusion of Young's double slit experiment right there. Light must be a wave. Section 23.3, Gradings, an application of interference. Explain what diffraction grading is. What advantage do diffraction gratings provide over simple double slits? Let's take a look. A grading is simply a surface with a large number of narrowly spaced slits. So in other words, not just 2 slits, but maybe 10,000 slits in a 1-inch spacing or more. Grading can be used to analyze the wavelengths of light emitted by biological materials or the wavelengths emitted by particles in the Earth's atmosphere or even stars and galaxies. Let's take a look and contrast how the intensity of light in a double slit experiment how that compares and contrasts with the diffraction grading. The first thing we should know is that both cases where it says m equals 0, you're going to have a central maximum. That means you have a point, a region of constructive interference, so you would expect to see, light shown and the intensity of light shown. So I'm going to draw that over here. I'm going to draw a minimum right here, a minimum right here. I'm going to draw a maximum right there, right above m equals 0. But I'm also going to draw a maximum right above m equals 1 and above m equals 1 on this side too. And notice I'm going to keep the level of the intensity pretty much the same for a double slit experiment. So now I'm just going to kind of connect these, and I'm going to have what the intensity of the graph ought to look like. How does this differ for diffraction grading? Well, I'll tell you, the diffraction grading still, if it's the same source of light, say it's the same color laser, same wavelength, it's going to produce the same intensity of light on the screen. So the level at which I draw it to is not going to change. But with more slits and more spacing, you are going to have more sharply defined intensity marks, and there's going to be more of them, essentially. But the way you would see it differently is you would not see it as a broad region of bright light on a screen. You would see it as a very skinny dot or a very skinny line on the screen. So I'm going to draw that here as well. So we have a maximum, we have a maximum, we have a maximum right at m equals 0, m equals 1 equals 1. We still have a minimum, but the minimum is going to be longer this time. So our maximum is going to look like this, really super skinny, tall, back down again. There's our minimum. And we're going to go really super skinny, tall, and there's our minimum. So notice the difference between how the bright fringes would look. The bright fringes for a double slit are going to be a lot wider. The bright fringes for diffraction grading are going to be a lot more narrow. In this example, to test new laser design, a lab technician sets up an experiment using diffraction grading and photographic plate. The diffraction grading consists of slits separated by a distance of 2 × 10⁻⁵ meters. Let's note that. the distance between the distance between the slits, okay, so this is diffraction grading, the distance between them, d, is 2 times 10 to the negative 5 meters. The photographic plate is positioned 2 meters behind the grating. Well, that would be L. L is the distance from the slits to the screen. The laser light is directed through the diffraction grating and exposes the photographic plate. A negative of the photograph is shown. What is the wavelength of the laser light? So lambda is the unknown. Well, here's what I'm going to do. Well, we're missing this. The equation we're going to use, of course, is m lambda L over d. And I'm going to choose the distance from 0 to the first bright fringe. So I'm always going to let m equals 1 unless the problem tells me to specifically focus on a particular bright fringe. So I'm going to focus here. Here is the central maximum. Here is the first bright fringe of m equals 1. And that distance right there would be 2 centimeters. So x would be 2 centimeters, which if you convert it to meters, because everything else is in meters, it would be 0.02 meters. I should probably write it like that. Now we want to solve this equation for lambda, okay? And again, we're letting m equal 1. So to solve for lambda, we need to multiply by d and divide by L. So lambda is equal to d times x divided by L. The distance between the slits is 2 times 10 to the negative 5 meters times x, which is about 0.02 meters, divided by L, which is 2 meters. Okay, plug that in our calculator. 2 times 10 to the negative 5 times 0.02. Divide that by 2. So 2 times 10 to the negative 5 times 0.02 divided by 2. Well, we get 2.0 times 10 to the negative 7. Now, keep in mind, should get in the habit of converting this because this is in meters, right? If I move the decimal place over twice, this becomes 200 times 10 to the negative 9. Moving the decimal this way twice moves the exponent twice. And you guys should remember that 10 to the negative 9 is nano. So in other words, this is 200 nanometers, which would most likely be ultraviolet light. In this example, a transmission diffraction grating with 600 lines per millimeter is used to study the line spectrum of light produced by a hydrogen discharge tube with the setup shown. The grating is 1 meter from the source, a hole at the center of a meter stick, and the observer sees the first order red line at a distance of y sub r equals 428 millimeters. What's the wavelength of the red light? Let's start that. So we know that the distance, the grating is 1 meter. You can see there's L. So let's list our variables. L is 1 meter. In this case, it's y. It's not x, it's y. Y is 428 millimeters. You have to remember, we got to convert it, right? So to convert from millimeters to meters, we have to go 3 decimal places to the left. This becomes 0.428 meters. We also have this value here, 600 lines per millimeter. Now, that's going to help us find D. The distance between the slits can be found by taking the inverse of that. Okay, in other words, if I want to know if I have 600 millimeters, or 600, sorry, lines per millimeter, and I reciprocate this, I take the inverse of this, then I'm going to get how many millimeters, I'm going to get how many millimeters there are in 600 lines. And if I divide by 600, I'm going to get the number of millimeters per line. In other words, I will get the slit spacing. So the easiest way to remember when we have the diffraction grading slit spacing written as lines per millimeter or lines per meter or centimeter, take the inverse of that and you'll be able to find it pretty easily. So the inverse would be 1 over 600 lines per millimeter. Now taking the inverse of 600, we get about 1.00167 millimeters per line. That's what we get. But I don't want millimeters, I want meters. So I need to, again, move this back 1, 2, 3 times. Okay, and my distance D is 0.000000167, which would be 1.67 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the negative 6 meters. So there's our distance D. Instead of x, it's y equals, and again, I'm going to use m equals 1. This is the first order red, so m equals 1 there. So m lambda L over D, let m equal 1. And again, solving for lambda, it's going to be D times y divided by L, where D would be 1.67 times 10 to the negative 6 times y, which is 0.428 meters. Divide that by L, which was a 1 meter separation. So 1.67 times 10 to the negative 6 times 0.428 divided by 1, we get 7.13 times 10 to the negative 7 meters, which is 713 times 10 to the negative 9 meters. And then, of course, you guys remember negative 9 is nano, so this is the same thing as about 713 nanometers, which makes sense because if we read the question again, first order red. Okay, this is a red bright light that's being shown. So the wavelength of red is approximately 700 nanometers. So that seems to fit. Qualitatively describe how the value of y that was measured will change when each of the following cases justify your answer. So again, x is equal to m lambda L over D. But really what we're talking about is x is proportional to lambda L over D. So let's look at each case. The diffraction grading and the I, really it's the diffraction grading, the I doesn't matter. The diffraction grading is moved backwards. So what this means is as L gets larger, X also gets larger. They're directly related. The distance between bright fringes will increase. If the diffraction grading is replaced with a new grading with more lines per millimeter. Okay, let's think this through. You had to take, to get D, you had to take the inverse of the number of lines per millimeter. So if we're talking about more lines, the inverse of more lines is a smaller number. Okay, just to prove that, let's say we had 800 lines per millimeter, and I'm going to compare it. I'm going to compare it to 6. So the original was, the original D was 1 over 600 lines per millimeter, which came out to about 0.00167 millimeters per line. That was the split spacing distance in our problem. Let's say we increase it to 800 lines per millimeter. Okay, so in other words, we put more. So 1 over 800 lines, that's going to be a smaller value because you're dividing by a bigger number. Right? If I take the inverse of 800, right, sure enough, I'm getting about 0.00125 millimeters per line. So, in other words, as D increases, the distance between adjacent bright fringes also increases. And what if the person measures a purple line? Well, purple, very close to violet. Okay, so what we talk about is we're talking about going from if we go from red to violet, essentially, purple is very close to violet. What's happening is we are decreasing the wavelength from 700 nanometers to about 400 nanometers. And decreasing the wavelength will cause the distance between adjacent bright fringes to decrease. They're directly related. Section 23.5, Diffraction of light. What is the equation that finds the locations of bright and dark spots for a single slit diffraction? Explain what M results in bright and dark locations. To visualize this, let's take a look at an animation to put the variables in action. Okay, so in this applet, we're going to take a look at single slit diffraction, similarities, differences to double slit and diffraction grading. What are some of the patterns we notice? Well, the variables are still very much involved, okay? Still have wavelength to account for, still have slit screen distance to account for, but this time, instead of the distance between slits, you have the slit width, the width of the one single slit. So let's begin. If we start off here with violet light and we increase the wavelength, you can see increasing the wavelength, and you can look, we see one bright fringe and it's very wide. By increasing the wavelength, that bright fringe just gets wider and wider and wider and wider as you get to, through violet to blue to green to orange to red, the bright fringe just gets wider. So what that means is as the wavelength goes up, the distance between bright fringes also goes up. Slit to screen distance. As that goes up, you can see the bright fringe is also getting wider, but it's very broad. It's not sharp at all. It's very broad. Okay, and so the distance between adjacent bright fringes is also getting farther apart. If we take the slit width and we make sure that it is, and we increase it, well, notice what happens. Increasing the width decreases the what we're looking at here. So we can easily change the equation accordingly. Let's take a look at how the equation will differ for single slit diffraction. And if we also look at the results of the experiment, we can see very clearly that you have essentially one large central maximum corresponding to that one bright fringe you see in the middle. But let's say we put a bunch of bright fringes in there, like this. Notice how each adjacent bright fringe on either side of the central maximum gets dimmer and dimmer and dimmer. That tells you something about the intensity. The intensity is very sharp for the central one. It's very wide, but it gets more narrow as you spread out, and the intensity falls off closer and closer to zero, meaning you're not going to see as many bright fringes clearly with single slit diffraction. And so instead of d sine theta equals m lambda, or d sine theta equals m plus a half lambda, if we're talking destructive interference in dark fringes, you can see d is just simply replaced by w, which is the width of the fringe itself, the width of, not the fringe, the width of the slit itself. In addition to that, you should also notice that the equation for this would also be x equals, if we're talking about the distance between bright fringes, m lambda L over w, not over d. D is no longer a variable, w, or the width of the slit, would be. And this, of course, would be x is equal to, or y if you're talking about vertical, would be m plus a half times lambda L over w instead of d. Okay, so let's compare what these intensities would look like again. So we did the first two already. Okay, in fact, I'm just going to go up a little bit, and I'm just going to copy that directly because that really didn't change. So I'm going to do that. I guess that didn't work out too well because the bright fringes are closer together. Okay, I'll redo the picture. So in the case of double slits, what do we notice? We should have a common intensity all the way across. Maximums at m equals 0 and 1, minimums halfway in between. And we simply connect those, and we get our intensity model, the light intensity for a double slit type of interference. Notice the width of these bright fringes, right? As opposed to diffraction grading, which carries with it the similar intensity. So we have maxima at 0, 1, and 1, but it's very narrow. How does that contrast with what we saw with single slit? Well, here's what it would look like. You'd have your maximum intensity, and you would have a very wide central maximum. And you'd have a minimum in between, just like before, but you'd have another maximum that's very short, like this, like this. And so you'd end up with something that is looking like that. With a large, wide central maximum and other maxima that are not quite as tall, which means the intensity of the light is not as bright. We're going to skip the width of the hair activity. Section 23.2, Index of Refraction and Light Speed and Wave Coherence. Well, when a wave of light goes from one medium, N1, to another medium, N2, the frequency does not change. However, the speed and the wavelength will change. The basic equation that relates the index of refraction to the speed of a light wave is n equals c over v, where n is the index of refraction, c is the speed of light in a vacuum, and v is the speed of light in a medium. The equation that relates the incident and refracted wave speeds, v1 and v2, to n1 and n2 is v1 to v2 is proportional to n2 over n1. Similarly, if we relate the incident and refracted wavelengths to the indices of refraction n1 and n2, then theta 1 to theta 2 ratio is proportional to n2 over n1. The index of refraction depends on the substance of the medium and is made up of wavelengths of the light. Briefly describe an experiment that can show the different colors that light has a different index of refraction even in the same material. Well, that's a pretty easy one to do. What we would do is we would take a prism, take a, say a triangular prism, and we would pass white light through that prism at an angle measured with the normal right there. This is white light. That white light is going to bend and refract a little bit inside, because there's our theta 1 and our theta 2 and so on. But then it's going to reach this point here where we get to this particular surface and we have a brand new normal. And we're going from inside the prism to out, so we would expect the light to refract farther from the normal, like this. And indeed it does. However, what we find out is that that white light, which is the sum total of all the different colors of the visual spectrum, spreads out into red, orange, yellow, green, blue, and violet. And so we find that violet has a greater angular deflection of the refraction than does red. Why? Because violet has a higher index of refraction in the same material than red does. Moral of the story, of course, is each color has its own frequency, its own wavelength, and thus its own index of refraction, even in the same material. Section 23.4, thin film interference. Thin film interference represents the last application of physical optics wave interference. Thin film interference is typically visualized with things like an iridescent or rainbow appearance. And where would we see this iridescence or this rainbow appearance? You might see it on a soap bubble. You might see it on oil on top of water. If you've ever looked on a rainy day and you see a puddle of water near the side of the street where cars parked, where the oil has collected, you see this iridescent glow of many different colors that sort of blur together. You also see this if you take a CD or a DVD, or even a Blu-ray for that matter, and you flip it on the silver side. You're either going to see silver, which is of course no reflection of light, or you're going to see a bright portion of the color spectrum of the rainbow, meaning you're going to see a rainbow appearance, or you're going to see the silver in between. So what we're going to talk about is anytime we're looking with the rainbow appearance, that means we're talking about constructive interference of reflection. Light is constructively interfering, and the reflected light, is constructively interfering and showing itself as a rainbow type appearance, a very iridescent glow of various colors. Destructive interference would be no rainbow, okay, no color. All right, so let's just make sure we understand what would a constructive interference case look like, visualize what it would be, and what would a destructive interference case look like? What would it be? And really there's 4 different cases that you could come up with, but really it comes down to 2 possible equations. So I'm going to show you how you can derive the equation yourself. Here's what you end up with. You have a place where a wave comes in. Now the wave itself, if you look, the wave here is coming in, and you can see it's entering the film. Okay, it's entering a thin film, like maybe this is a case where we have, let's say, air, oil on top of water. That would be a case there. And what you have is you have the air, the wavelength is getting smaller when you get into the oil, and it's getting even smaller when you get into the water because the index of refraction is getting higher and higher, right? The index of refraction starts low and it goes higher and higher as you go from the film to the water. Now, what ends up happening here? What we're going to do is we're going to look at a model of how waves interact with a boundary. And that's going to help us be able to derive and determine what the equation will end up looking like. Let's take a look at this animation. So in this animation, we're going to look at the transmission and, more importantly, the reflection of the wave from either a free end boundary or a fixed end boundary. And that is going to translate itself to waves that reflect off higher or lower mediums of the index of refraction is either higher or lower in the next medium. So we're going to make that comparison shortly. But let's take a look and observe. When a wave is sent and reflects, notice the free end boundary, it kind of just goes up and down again. When it reflects off a free end boundary, it reflects in phase. You can see the wave pulse is above the horizontal line, and it simply reflects above the horizontal line. So when waves reflect off of a free end boundary, they're going to reflect back in phase. So let's remember that. Let's take a look at fixed end reflection. It's reflecting off a wall, a barrier that cannot move. Notice the wave pulse comes in above but reflects below. You're reflecting off of a higher, you're reflecting off of a fixed boundary, and you're reflecting out of phase instead of in phase. So let's translate what we just saw to how light reflects off the top and bottom of a thin film. So here, I'm highlighting it right now. Here is our thin film right there. It has a top boundary and it has a bottom boundary. And light is going to reflect off both of them. So what we see is if we're going from n equals 1 or n1 and the index of refraction of the film is higher, what are we doing? We are reflecting. Notice we come in this way, and this end of the wave is meeting the exact opposite end of the wave. You're reflecting out of phase. We are reflecting out of phase. Okay, but notice at the bottom boundary as well. The bottom boundary, what do we have? N2 is higher than N of the film. And notice we're also reflecting out of phase compared to the original incident wave. So both reflections are out of phase. Now keep in mind, they're out of phase with the original incident light. However, since this is out of phase and this is out of phase, they're actually in phase with each other. So in this case, the reflections are in phase with each other. And how does that translate to a relationship? Well, here's what it looks like. The light, when it passes through the film, is going to pass through this right here. This is going to be T, and T is going to represent the thickness of the film. Okay, it's a lowercase t, kind of like time. But the light passes through the thickness of film once and then twice. So the relationship is going to be 2t. But what does 2t equal? Well, it's the thickness of the film relating to, if they're in phase with each other, then that means they are off by some multiple of wavelength. It means they are constructively interfering. That's a pretty important point. If the reflections are in phase with each other, they're constructively interfering. So what do we see? We see rainbow, right? We see rainbow colors. And it means that twice the thickness of the film is going to be, in other words, the distance going down and then up again through the film is going to be some multiple of lambda. Now, again, you don't really need to use m quite that often, so I usually just put m equals 1 into that reflect. But the m corresponds to the different possible bright colors of constructive interference that you could account for. So in other words, all the different color portions that ends up showing up. And so I'm not really interested in that per se, as I am just, are we getting rainbow color or are we getting no color? For instance, if it's a DVD, are we getting that rainbow color or are we getting just the silver, which is no rainbow color? So it's rainbow color or no rainbow color. Well, we are getting rainbow color here. So this equation simplifies to 2t equals lambda. Now we better be careful. This is lambda n. Lambda n is the wavelength, or is the wavelength in the film, in the medium. And if you recall, the n is equal to lambda O, this is the vacuum wavelength, or the wavelength of light in air, over lambda n. So if I were to rewrite that, lambda n is equal to lambda O, which is the vacuum or wavelength in air, over n. So if I replace this with this, the equation could look like 2t equals lambda O over n. And if I multiply both sides by n, I get 2nt is equal to some multiple of a wavelength. You can either use this equation here or this equation here. It really depends on if you're given the wavelength in the film or if you're given the wavelength in air. Okay, and we're gonna practice that fact. Now let's look at the other cases and see what the equation is that we derive. And you always want to try to derive the equation. Don't memorize it. Try to derive the equation based upon how the reflections are interacting with each other. Compare the reflections to each other. Okay? So again, when you reflect off of a medium with a higher index of refraction, you will reflect out of phase. Consider that like the animation we just saw. When you reflect off a fixed boundary, the wave reflects out of phase. So think of a medium of higher index of refraction. It's more optically dense. It's harder, light is harder to pass through. Think of it as a more fixed boundary. So light is going to reflect off of it out of phase. So if I reflect off the top and bottom part of the film with higher indices of refraction both times, then both times we reflect out of phase. However, as we talked about, if both of them are out of phase, they're really in phase with each other. That's the important point, is compare whether or not they're in phase or out of phase with each other. That helps you derive the equation. In the second example, the incident wave comes in, and if you look, it says n of the film is greater than both n1 and n2. So I would actually write it like this. n1 is less than n of the film, which is greater than n2. So this is going to be the greatest one. And what could this be like? This could be like a soap bubble. Perfect example. What would a soap bubble be? A soap bubble would be air, soap, and air again, right? That's what a bubble is. It's air inside of a soapy film, and then outside of it is air. So that would be another example we could see. And what would that look like? Well, in this situation here, n of the film, right, is greater, so n of the film is greater than n1. So in this case right here, since this, so this is my value for n1, my value for n of the film is greater, so I'm reflecting off a more optically dense medium. What does that mean? I reflect, I'm going to move the soap bubble out of the way here. I will reflect out of phase. So this reflection is out of phase compared to the incident wave that reflects off that top part of the film. So here's the top part of the film, here's the bottom part of the film. Now if we look, the bottom medium is less than the index of refraction of the film, which means this is like reflecting off a free end boundary, not a fixed end boundary. And when that happens, you reflect in phase, not out of phase. So you can see the incident wave that comes in, the reflection off the bottom produces a wave that is completely in phase with the original wave that came in, the incident wave. Which means this is in phase. So when I talk about out of phase and in phase, I'm talking about out of phase with the incident light, in phase with the incident light. Now, how do they compare with each other? Well, if one reflection is out of phase and the other one is in phase, this means the reflections are out of phase with each other. Which means this is T, this is T. Put that together, we get 2T equals, well, out of phase. If they're out of phase with each other, then that means that there is a difference of half a wavelength. Or, remember, you could write it as 2NT is equal to this is the wavelength in air, this is the wavelength in the film. But notice it's half a wavelength. Okay, and when you use this, you need to remember that that's the index of refraction in the film, not in air. Okay, now what would happen if if the n of the film is less than both? What would that look like? Well, that would be something like glass. So say, for instance, we had glass, a little air, and then glass again. Right? You could make this very easily by having, say you had like a thin piece of glass, like a microscope slide, and then you put one end of it just a little bit higher, put like a wedge in the side and create an air pocket in between, and the light will end up showing, if you look at it over the top, it will show a nice iridescent pattern. But let's take a look at how that would end up being. The N1 is much bigger than N of the film, and N2 is much bigger than N1. So we're reflecting off a smaller index of refraction. So we are reflecting in phase. You're reflecting in phase. Off the bottom, well, off the bottom, N2 is greater than N of the film, so you're reflecting out of phase. We're reflecting off a fixed end boundary. Think of it that way. Okay, now how do these compare? The reflections are out of phase with each other. This helps us derive the equation. 2t equals half a lambda. Or 2nt equals lambda O over 2. Depends if we're talking about using the wavelength in the film or the wavelength in air. And lastly, what if you're going kind of in reverse order? So say you're going from a high index of refraction, the film is lower, and N2 is even lower. Now, I can't really think of a situation where this would be visualized unless you had, maybe you had an oil slick on water and you were shining laser light from underneath the water, or some sort of light from underneath the water, and you were visualizing it from underneath the water. It's possible, I suppose. But notice what we're doing is we're reflecting off a higher index of refraction here, and then you're reflecting off an even higher index of refraction for N2 also. So what would this look like? Be kind of like water, oil, air, but looking at it from underneath. I guess you could think about it that way. So I'm reflecting off a smaller index of refraction. So I'm reflecting in phase. This wave is reflecting in phase compared to the incident wave that came in. This N2 is also smaller than N of the film, because remember, you talk about the reflections off the top right here and off the bottom of the film down here. And since you're reflecting off of a lower index of refraction in medium 2, you're also reflecting in phase. How do these compare? Well, if both reflections are in phase, then both reflections are in phase with each other. Which means 2t equals lambda, or 2nt equals lambda O. Again, air wavelength, film wavelength. Let's take a look at an example. A 600 nanometer wavelength travels through air. The normally incident on the thin film, the film has an index of refraction of 1.5, and the other medium, the second medium, has an index of refraction of 1.2. So we're going, if we reflect off the top part of the film, so what we're going to do is we're going to look at the reflections. So the reflection off the top part of the film, you're going from 1 to 1.5. So you're reflecting off a higher index of refraction. So off the top of the layer, off the top of the film, we're going to reflect out of phase because you're reflecting off a fixed, rigid boundary. So we're going to reflect out of phase here. Now the bottom part of the film, when it passes through, right here, it's going to reflect, you're reflecting off a smaller index of refraction, which means you're reflecting off of a weaker boundary, a more free end boundary. You are going to reflect in phase compared to the original incident wave. How do these compare? Reflections are out of phase with each other. What's the frequency of light in air? Well, n equals, and actually no, I should use the speed of light is equal to frequency times wavelength. Frequency would be the speed of wave in a vacuum over the wavelength. So the speed is 3 times 10 to the 8 meters per second. Over the wavelength, 600 nanometers, I can rewrite that as 600 times 10 to the negative 9 meters. You have to be able to rewrite it in meters. And when we throw that in our calculator, we get a frequency approximately 5 times 10 to the 14 hertz. What are the wavelengths, frequencies, and speed inside the film? Well, the wavelength, now is where we can use this equation here, n equals lambda O over lambda n. This is the wavelength in the film. Switch them. And lambda n equals lambda O over n. That would be 600 nanometers, keep it as nanometers, divided by the n of the film, which would be 1.5. Well, that means the wavelength in the film would be about 400 nanometers. That makes sense in the picture we saw earlier, right? If n is a higher index of refraction than n1, the film, you can see the wavelength is getting smaller. The speed, how do we find the speed? Well, n is equal to c over v. V is the speed of light in a medium, so v is c over n. So we take our speed of light in a vacuum or air, 3 times 10 to the 8 meters per second, and we divide that by the index of refraction of the film, and the speed in the film gets reduced to about 2 times 10 to the 8 meters per second, about 200 millimeters per second. And the frequency remains constant. So the frequency is still 5 times 10 to the 14 hertz. That remains constant. What that basically means is the number of waves doesn't change. Only the spacing of the waves and the speed of the waves change. At which interfaces do we have a 180-degree phase shift? Well, you're only out of phase on the top. So there's your 180 degrees phase shift. This would not be. So only in the interface between N1 and the film where you're reflecting off a larger index of refraction. And D, what is the minimum thickness that would produce constructive interference? What does that mean? That would produce a rainbow, right? Constructive interference means what produces the rainbow. Okay, so what's the minimum thickness to produce the rainbow? Well, 2t equals lambda n. Okay, t would be essentially lambda n divided by 2. Lambda n was 400 nanometers, if you recall, we solved for that in part B, over 2. So the thickness of the film to produce this rainbow appearance would have to be about 200 nanometers in thickness. All right, well, thank you for being patient with this process. These are very difficult concepts. Please make sure that you pause and rewind the video as necessary and ask as many questions as you need to. Thank you and goodbye.